So if you remember back when you guys did enthalpy and thermodynamics, you probably talked about enthalpy in the terms of heat. And so heat exists everywhere, and heat is exchanged in solutions and reactions. And so we can do the same thing when we're talking about the individual enthalpies and the interactions between solutes and solvents. So we're going to break it down. So there are 3 steps involving energy in the formation of a solution. So there's the separation of solute molecules. Or step 1, I have a beaker, imagine again, of water. I pour NaCl. There requires energy to break the bonds, because remember, this breaks into 2 ions, Na plus and Cl minus. And so it takes energy to break the bond between the Na plus and the sodium atom and the chlorine atom. That's the enthalpy number 1. The separation of solvent molecules. So this sounds a bit weird, how we're talking about the separation of solvent molecules, because it's not like we can just break water up into like H and OH. Although that happens with the autoionization of water. You'll learn that about in acid-base chemistry. But what this essentially means, water molecules have a tendency to really latch onto each other because of the momentary the hydrogen bonding that happens between the net positive and net negative dipole moments within the water atom. So although we can't, physically break the bonds, we can, however, with NaCl, remember those hydration shells I was talking about earlier, we can basically take these water molecules will be less inclined to really have electrostatic forces between each other and more inclined to really to surround themselves around ions. And the formation of the solute-solvent interaction. So that's what I was talking about earlier. So the first is breaking of the sodium and the chloride. The second is the energy needed to break apart any electrostatic forces between the interacting solvent molecules. And finally, the last phase, as I mentioned before. So if you have a sodium ion, of course the reverse is true for chloride, because the net positive hydrogens are going to face these chloride minus. Yeah, and the enthalpy of the overall solution can be positive or negative depending on the intermolecular forces. We're going to talk more about them in detail. So there's a famous phrase. In AP chemistry for describing endothermic processes. It takes to break. And so remembering this allows us to think about solutions and breaking bonds individually. So step 1 of the enthalpy process is expanding the solute. And by expanding, we mean the breakage of bonds. So this requires energy to be added to the system, and so that is endothermic. And so the magnitude of the value is high in ionic and polar slice, because those electrostatic forces are really close together. In really polar substances such as water, those electrostatic forces between them are very high. And of course, because of ionic compounds, remember Coulomb's law. This connects all the way back to unit 1, 2, 2. Where we talk about how ionic compounds have a very high electrostatic force between them, because either the charge is really high or the radius between them is really small. And finally, the interaction of a solute and a solvent to form the solution. So when energy is released, how I learned is that the system is relieved, and so it relaxes, and so what happens is that it releases energy because it has achieved a more stable state. And this, formation of solution will produce a higher final energy state. So the magnitude of this value is high in polar solute, polar solvent interactions, and it's low in other types of interactions. Remember, like dissolves like, which is the classic saying for polarity and solubility. So if you have a polar solute and a polar solvent, those are gonna be miscible, meaning they can mix with each other really well, and so it will have a high exothermic reaction because it is more stable.